All right, now that we've looked at how perturbation theory works from two different points of view, I want to spend the next part of this lecture talking a little bit about vowel systems, or sort of the structure of vowel systems, and how we articulate vowels affects that structure cross-linguistically. So let's think briefly again about the cardinal vowels, and I pointed this out, I think, when we were reintroducing them in the previous lecture. So they're a little bit weird because they're supposed to sort of define the parameters or the two-dimensional space of the vowel articulatory system. And they start out with like cardinal vowel number 1. E is the highest frontist vowel you can produce, but it's unrounded. And then it swings around to vowel number 5, which is like ah, which is like the lowest backest vowel you can produce, which is still unrounded. But then all of a sudden when you get up into 6, 7, 8, then all those vowels are rounded. Wouldn't it have made more sense to like make the primary cardinal vowels all unrounded maybe, and then all the secondary cardinal vowels rounded? But no, they're mixing, or Daniel Jones mixed both rounded and unrounded vowels in the same space. So why are those high back vowels rounded and everything else unrounded? We know at this point that rounding back vowels takes advantage of an acoustic synergy. So rounding vowels in general is going to lower F1 and F2, and we just looked at sort of that new representation of the standing waves in the vocal tract, and we found that if you produce like a velar style articulation, that should lower F1 and F2 as well. So doing both of those together gives you synergy, right? They're both going to lower F1 and F2. And in an acoustic space, that's going to push a vowel up into that high back corner, closer to this kind of the 0-0 origin of the measurements of F1 and F2. So this is a plus when you can get two things to work together. But is there anything wrong with rounding the other vowels? Why don't we seem to get those quite as much? And to kind of introduce this concept, I'm going to go back to something I talk about in 341, which is that we tend to see patterns in the vowel spaces of the languages of the world anyway. So why are we getting these patterns? There are some languages which just have 3 vowels, something like e, u, ah. A really popular vowel space option is to have 5 vowels, e, u, a, o, ah. My wife speaks Ukrainian natively. Ukrainian basically has 6 vowels, like e, u, ah. These are kind of low mid, like e and o, open o. And then it squeezes in another vowel here in bard I, which is hard for me to produce accurately on the fly. But 5 vowel spaces are really common, and they're kind of normally lined up in a triangle like this, almost like a rack of bowling pins at the bowling alley without the sort of ones you can't see in the middle. So here's some examples of this. Here's Spanish. These are 4 languages. I mentioned this before. These are 4 languages which are geographically in totally different parts of the world, or originally from totally different parts of the world. And historically, they don't really have any genetic relationship with each other, as it were. So here's Spanish with these 5 vowels.
Masa, mesa, misa, mosca, musa.
We'll turn that up a bit. Here's Swahili.
Pata, peta, pita, pota, puta.
Here's Hawaiian.
Kaka, keke, kiki, koko, kuku.
And here's Japanese.
Ma, me, mi, mo, mu.
Okay, so these go by a little bit more quickly. This last u in Japanese is often transcribed as an unrounded u. So maybe this one's a little bit different.
Ma, me, mi, mo, mu.
But same general idea. You have 5 vowels kind of arrayed around the perimeter of the space. Here's another example. This is from a student project that was done the first year I ever taught this class. This is Gujarati, which is spoken in India, or at least originally. And this has 1, 2, 3, 4, 5, 6, 7, 8 vowels, which also kind of form a triangle, which is cool. And then it has schwa in the middle here. And this student, back before we had tools like R to graph things for us, plotted these, measured these vowels as they were produced by his consultant, and then arrayed them all in a little Excel graph, and this is what he got. So it's nice and symmetrical, more or less, even though it's real data, which is often pretty messy. What you don't normally see is something that is a mess in the vowel system of a language. You don't normally get 5 vowels arrayed like this, like e, I, a, and they're all kind of here in the front. Why is that? I think you know the answer to this, even if you don't want to say it out loud, because that would mean you'd have to speak to a talking computer, and normally people don't do that. But I think you know the answer, which is that these are just pointlessly close to each other, right? It would be a lot easier to sort of perceive the differences between these vowels if they were more widely spaced in the vowel space, right? And there's nothing really constraining you from producing backer vowels or other low back vowels here. So why not use this space that's available to you rather than crowding everything together in the front? The analogy I like to give for this is like if 5 people were to enter an elevator, they would not all sort of crowd, towards one side of the elevator right next to each other, especially if they didn't know each other, right? They'd probably want to space out more or less as much as possible within the small confines of that space. Vowels do the same thing as people on an elevator, and the name for that idea is called adaptive dispersion theory. This was developed by a couple of Swedish speakers named Björn Lindblom and Johan Liljekrantz about 50 years ago. Why they're Swedish speakers is something that'll become relevant here in a second. And their theory says that vowels should be as acoustically distinct from each other as possible. Or basically, even more broadly, they believe that speakers are trying to produce distinct vowels so that their listeners can understand what they're saying. We speak in order to be heard, in order to be understood, is kind of the basic functional foundation of their theory. You're speaking for a reason, which is to talk to other people. Whether or not they're listening is up to them. Okay, so languages are supposed to maximize the distance between vowels in acoustic space. When it's not easy to find space for different vowel categories, you can lose a distinction. So like ah and aw, or maybe ah and aw, are vowels which are not consistently distinct in Canadian English. Acoustically speaking, they're very close to each other. It would be easier to maintain that distinction, according to this theory, if you had more acoustic space between the two elements of that contrast. So here's Swedish, and this may be why they were inspired to come up with this theory, because Swedish has more vowels than any other language I know or have heard about. So I'll play all of these for you, and you can sing along if you want to, just for kicks, because why not?
Rita,
Whoop. Make that a bit louder.
Rita, reta, räta, här, ritt, rätt, ryta, ruta, röta, hör, nytta, rött, rött, rota, råta, rata, rot, rått, ratt.
All right, there's a lot of vowels in there, and I think some of them probably sound pretty similar. I could even just go across the top here.
Rita, ritt.
Do those two vowels sound different to you? I don't know.
Rita, ritt.
Those are pretty similar too.
Nytta.
There's not a lot of space for these to sort of expand and stamp out their own spots in the acoustic vowel space, and therefore they become difficult to tell apart from each other. It's probably a lot easier if you speak Swedish natively, but I don't, and I'm guessing you don't either. It's actually fairly uncommon for students in this class to speak Swedish, although who knows, there's probably a few. Anyways, I'll give you some numbers. These are collected from the UPSID database, which I've talked about on many occasions before. So there are 316 languages in the UPSID database, and out of those languages, these are the number of languages which have these different vowels. So this is the set of unrounded vowels in the IPA chart, like E, A, so on and so forth, and the unrounded central and back vowels too. And you notice that there's a fair number of languages which have unrounded front vowels. I've got this special notation in here. Some languages have a contrast between A and E, like in English, but other languages don't, and they just kind of have a vowel, which could be either one of these, and so I put those in parentheses. But there's a lot of languages with a vowel in here somewhere. There's a lot of languages with like a low central vowel, like ah, could be maybe fronter or backer as well. But there's not many languages with these vowels, these back unrounded vowels. There's just a handful, really, out of 316. And you can contrast that with the rounded vowel stats. So we have a lot of vowels back here. These are common, oo, o, o. And then there's even some languages which don't really have a contrast here. There's a lot of oo's as well. Everything else is small in number. So only u and have more than 10 languages with those vowels. The rest are just tiny numbers. And there's no languages which have this vowel as far as we know, which is kind of funny, right? So this symbol really only exists in the IPA because Daniel Jones wanted it to be there to sort of provide him with a symmetric set of vowels for his cardinal vowel system. There had to be something here for the unrounded vowels, so when he made the secondary vowels, he needed to have a counterpart for the a vowel, and he made this one. But no other language has done that, so it's kind of an artificial vowel, as it were. If you divide the number of rounded vowels by unrounded vowels for any particular spot in the IPA chart, you get these numbers. And you can see that the rounded numbers, or languages with rounded vowels, severely outnumber the ones with unrounded vowels in these positions, even to the extent of, say, 63-1 for oo versus u. So if Japanese really has an u, it's really an outlier there. Also, o and o are a lot more popular options than u and even though some varieties of English have both o and but other than that, languages around the world will tend to prefer the unrounded variants. It's just in this spot up here that they want to have rounded vowels more often. And we can see that nice little 0 here where no language has a rounded vowel in this particular low front position in the space. Okay, so I want to kind of consider these 4 corners of the space again. We've talked about them already at some length, and just figure out why we're getting these patterns that we do. So at this position, oo is highly favored. The rounded version is highly favored. Here, there's a bias towards the unrounded version, although a few examples of the rounded version as well. Here, we're strongly biased towards having an unrounded vowel, and here we absolutely have to have an unrounded vowel for some reason. Why is that? Why are the numbers skewed in the 2 different directions depending on what spot in the vowel space we're dealing with? Okay, so I'm going to say that the vowels, the rounding type or the rounding specification for these vowels that is most common cross-linguistically is the preferred type of vowel, or you might consider this the good vowels, at least maybe according to the theory we just talked about in terms of adaptive dispersion theory. If a vowel is dispreferred, or if a type of rounding or unrounding is dispreferred in a particular position in the space, that's bad. A language wants to avoid that, more or less. So in the high front region of the vowel space, the good vowel is the unrounded vowel e, and the bad vowel is the rounded one u. In the high back region, the good vowel is oo. In the low back region, the good vowel is ah without rounding. Interestingly enough, a fair number of Canadians round this vowel and maybe don't have an unrounded version, or maybe they go back and forth between the 2, but rounding here is a little more possible than it is for, say, E. But where rounding is really not possible is that low front region. So that's a bad vowel. It's dispreferred across the languages of the world. Okay, so let's think about this. If we look at bad vowel number 1 in this high front region of the space, we don't get that many languages with this vowel. A fair number, but not that many, especially compared to the vowels, the unrounded vowels in this position. Why is this bad? So U has both labial and palatal constrictions. And I just realized it would probably be handy for me to actually write this out for you. So I think I'm going to pause here again, let you think about this. Actually, maybe I can get away with this. And you can think for a moment about what would happen to the formant frequencies of the vowel U based on perturbation theory. So U has both labial and palatal constrictions, right? So if we look at the labial constriction for F1 and F2, we have an antinode for both of those guys. I'm just drawing a little vowel space here on my whiteboard on the spur of the moment. And I'm going to get a red marker too. So if we have an antinode for F1 and F2 and we constrict there at the lips, that should lower both formant frequencies, right? So F1 and F2 should go down. If we have a palatal constriction, then that is near a node for F2 and near an antinode for F1. So this being at a node, that should raise F2 and it should lower F1. So I'm going to draw both of these out. Yeah, I've got my little vowel chart here. Maybe I'm not completely done with this guy, but I'll front, F2, back, high, low for F1. And I'm going to specify here again what we talked about before. My default value for F1 is going to be 500, but it can differ depending on who's speaking. And my default value for F2 is going to be 1500 hertz. So I've got a little vowel chart that looks like this. Hopefully you can see that reasonably okay. I'll try to make my portrait on this video big enough so you can see that. And we'll look at these two different articulations. So I'll plot the, I'll plot these, and I guess green and red. So if I am making a palatal constriction, then I should get the effects on formant frequencies that I expect for an E. So I'm going to get a lowering of F1 and a raising of F2, right? So there's my palatal constriction. It's going to push me in the high front region of the space. And then on top of that, what I'm going to do is also produce a labial constriction, and that should lower both formant frequencies, right? So if I'm doing that in conjunction with the palatal constriction, then I'm going to get two effects on my formants. The red one is going to be the result of the labial constrictions. It's going to push my formant frequencies lower for both F1 and F2. And if I do that, maybe I was trying to get to the high front region of the space, but it's going to push me a bit backwards in a central region, more or less, compared to E, according to this theory. And you can do that if you want to, but it's not going to get you as far to the extreme as not rounding will. So if I just don't round at all, I kind of wind up at the end of the green arrow, and I'm further away from the center of the space than I would be if I rounded that vowel. This puts me back towards the middle, kind of regressing to the mean around where all the other vowels are. So I'm a little more distinct here if I'm just not rounding. I'm getting a little bit further away from everybody else. I'm getting to my own little corner of the elevator if I do that. If I move back by lip rounding, then I'm getting a little bit closer to everybody. And who wants to do that? This is the era of COVID-19. You might get sick, right? That's not why it's happening. It's been happening for generations, we know. But that's the idea, is that what brings you closer to other vowels makes you less distinct and harder to understand and less likely to survive in a vowel system. And that's why U, the rounded high front vowel, is a little less common than the unrounded high front vowel, which is more often its own space. The other way to think about this is to just kind of look at what's going on with these constrictions. So especially for F2, this constriction at the palatal place of articulation should raise F2. This constriction at the labial place of articulation should lower F2. Why am I doing two things that have the opposite effect of one another? So with the other issue with the U vowel is I have to do two sort of constrictions, the palatal and the labial constrictions. And they both work at cross purposes for the F2 value of this vowel. For E, I just have to make one constriction, more or less, which is to make a constriction here at the palatal node for F2, or the palatal place of articulation. So I get a better acoustic effect with less articulatory effort for E. I have to put, on the other hand, more articulatory effort into an U, at least in terms of two gestures rather than one. And I get less of an acoustic benefit out of it because my F2 gestures are kind of canceling each other out. all I'm getting is a lowering of F1, basically. So that's why it's bad. More effort, less effect compared to an unrounded vowel for this place of articulation, or this part of the vowel space, rather. Okay, hopefully that makes sense. There's kind of two optimizing factors coming into play here. There's the articulatory side, which is that you don't want to put effort into something if you don't have to, and you really don't want to put effort into something if it's going to counteract another effort you're working on. And then there's the perceptual side of it, which is that you want the people you're speaking to understand what you say. And for that reason, you want to be able to keep things distinct. So let's look at bad vowel number 2. U is kind of dispreferred in contrast to U in that high back part of the vowel space, which has low F1 and low F2. Why is that bad? And this is going to be bad for a different reason. So I'll try to plot it out here. Let's say we're making this U with only a velar constriction. We're near an antinode for both F1 and F2. So that should lower both formant frequencies, right? And that should push you towards the back of the high back region of the space, which is good. We're getting more distinct here because we're getting away from schwa. But what we're not doing is what we would get for an U, which is rounding. So rounding will give us a constriction at the lips, and that's also at an antinode for both F1 and F2. So if I tag that on to my initial constriction, then I just keep moving further high and further back, further up and further in, right? So in that case, you're getting further away from everybody else. So you're more distinct with the two articulations for U than you are for the one articulation for U. So this turns out to be a case where our bodies and minds are willing to go the extra distance and produce the two articulations, because we wind up getting a doubling of kind of the acoustic effect, and we get further high and back here, more distinct from everything else. If we didn't do that, we'd still be generally heading in the direction of distinctness, but just not as far. So it turns out over time, languages evolve to sort of encourage that doubling up of the distinctiveness or the synergy involved in labial velar constrictions. So velar constrictions by themselves are bad just because they could make use of their similarities to labial constrictions, but they're not making use of that sort of synergy or that symbiotic relationship. Okay, so for bad vowel number 1, we had a problem where two articulations were canceling each other out. For bad vowel number 2, we had a problem in that we could be using two articulations that would work together, but we're not. And they're both bad because that leads to less distinctness for the two dispreferred vowels. We can look at bad vowel number 3, or the low back rounded vowel aw, which has a pharyngeal and a labial constriction. So what would we expect to get out of this? Our labial constrictions, once again, would lower both formant frequencies because they're both close to antinodes. Our pharyngeal constriction should give us the pattern we kind of expect for an ah, a low back vowel. So we're closer to a node for F1, so that should push F1 up. And we're closer to an antinode for F2, so that should lower F2. And we should go into the low back part of the space for that reason. So we have higher F1, lower F2, like that, which is what we get for ah, which is kind of what we're contrasting this rounded version with. What happens when we round this guy? We just said that we're going to lower both formant frequencies. So we're actually going to move a little bit away from that low back corner of the space. We're going to go a little bit higher and backer in terms of traditional vowel terms. We're going to lower both formant frequencies and not get closer to this corner of the space. This is where we want to be for distinctness. This is where we wind up with two articulations. And again, we're kind of winding up with the same problem as we had for E. We're putting extra articulatory effort into this, and we're getting worse acoustically. So this is going to be bad for two different reasons, right? We don't have as much distinctness, and we have to put more effort into it, so why bother? So this rounded version of this vowel is not as likely to be found in a language of the world as the unrounded version. Ah. Yeah. Like I said, though, this vowel kind of gets messy in modern varieties of English, so this is not an across-the-board absolute. It's just a pattern we find cross-linguistically. Lastly, we have this really bad vowel, or however exactly you say it. Maybe because it doesn't exist, it doesn't really matter. Daniel Jones is technically dead, so maybe we don't have to worry about him that much. But in this case, we have two different articulations. We have a glottal articulation and we have a labial articulation. We've seen the labial one for every single example, so we know the labial articulation is supposed to lower both formant frequencies. This glottal articulation is near a node for both F1 and F2 at the glottis, so that should raise both formant frequencies, right? So our glottal articulation will push us into that low front corner of the space, which is yay good because we're getting away from the middle, and that gives us more distinctness, right? But if we produce a labial constriction on top of that, then we just head back to where we came from, right? Because that's going to lower both formant frequencies. We're simultaneously going to be raising both formant frequencies and lowering them. And with two efforts or two gestures, we are going to accomplish nothing. It would have been easier to just stay at home and produce a schwa without having to worry about it. Just open up your mouth and phonate. This is not baseball. You don't get credit for like leaving home and then coming back. You want to have distinctness. You want to stay on second base or even further away if you can, right? So that's why that's really bad. You have a lot of effort. You have absolutely no acoustic benefit in terms of distinctiveness. So nobody uses this vowel except Daniel Jones. And I know I said he was dead, but he obviously lives on because this vowel lives on in the system too. So, yay. This is what phonetics gives you, is immortality in the world of phonetics. So that's all I'm going to say about these bad versus good vowels. And I think that's all I'm going to say about Daniel Jones in this lecture as well. So in the next part of this, I'm going to move on to some other features that we haven't talked about, other sort of diacritics and features of vowels in the IPA system that we haven't learned so far. And that'll be it for today. So see you again in a second.